It's time for our presentation with Rob Porter from Sony Europe. Now, he's going to be talking about scalability and performance of what we've just been talking about with IS-04 and IS-05. So this is really something that's a concern as these facilities get larger, traffic loads go up, and we'll hear a reprise of a very good presentation given the other day, and I think you'll find some good information in this. So take it away, Rob.
Thank you, Wes. Good morning, everyone, and welcome to this presentation on the scalability and performance of the IS-04 and IS-05 APIs and how TR 1001-1 helps. So just quick definitions here for those who aren't familiar. IS-04 and IS-05 are the APIs, the specifications developed by the Advanced Media Workflow Association for the discovery and registration and also the connection management of media nodes when you connect them to the network and how you make connections between senders and receivers. I'll go into that a bit later in the talk. TR 1001-1 is a new technical recommendation from the JTNM, and this is all about making networks and media nodes as easy as possible to configure. So when you plug things into the network, they should be doing things like DHCP, DNS-SD, not having to assign IP addresses to every single device individually. So TR 1001-1 has a series of recommendations. It's a JTNM document that's just come out, and you can find out more about it on the stand. And I'll talk about how that actually helps some of the scalability and performance issues that we have with IS-04 and IS-05 if we don't take on some of those recommendations. So my talk's in 4 parts. I'll start by briefly going over the APIs for those who aren't so familiar. I'll then define our scalability study and what we set out to do and how we did it. I'll then go on to give some results from the study, and finally talk about some best practice recommendations and how that TR 1001 document helps. So starting off with the APIs themselves. So this is a very simple recommendation, representation of our professional media network. It centers on the network infrastructure. So here this is represented by a single switch, but in reality this could be any architecture. This could be a monolithic switch or a multi-layer leaf spine network. And connected to that switch we have a series of media nodes there. So in NMOS terms, a node is a logical host connected to the network. A node itself can host one or more devices. So a device is a kind of logical block of functionality which could have any number of associated senders, receivers, sources, and flows. And in NMOS terms, these are all known as resources, and they're defined within the JTNM content model. So as an example, here's an IP-connected camera. We represent that as a single logical node connected to the network. Within that, we have a single device, a single block of functionality. That device itself has 2 senders. That could be an audio sender for the mic and a video sender for the camera. And with each of those senders, there actually be an associated source and flow, which I haven't drawn on there. The source is where that media originates from, and the flow is its representation, its encoding and so on, that the sender can make available on the network. Also within that camera, we have 2 receivers. So they're also part of the device. The receivers could be, for example, 2 video return channels, so they could be 2 video receivers. Another node example there is an IP multi-viewer. So here we've got a 3x3 multi-viewer. Each picture-in-picture within that multi-viewer is represented here as a separate device, and each device has 3 receivers, an audio receiver, a video receiver, and a metadata or ancillary data receiver. So those would be receiving, in SD2110 terms, -20, 30, and 40 streams from the network. Then the key part of IS-04 that we add to the system is the registration and discovery system, the RDS for short. So the RDS can actually comprise 1 or more registry instances, and each of those includes a database that stores all the registered resources on the network, those NMOS resources I spoke about. The RDS also exposes 2 APIs, which I'll go into a little more detail in a moment, the registration API and the query API. And finally, on our professional media network, we have an NMOS client. So this is the control system, something like a broadcast controller or a routing panel or routing panel. This is what we use to allow connections between the media nodes to be set up. So the IS-04 registration API. So when we first connect one of these media nodes to the network, first of all, it needs to discover the registry or the RDS, the registration and discovery system. And it does that by looking for advertisements done using DNS service discovery. Those could be multicast DNS advertisements from the registry itself, or they could be unicast using a centralized name server. Once the node has discovered a registration API, and it will choose the one with the highest priority, it will then register its node resource. It will choose the one with the highest priority and register its node resource with that selected registration API by making an API call. Once it's registered its top level node resource, it will then go on and register all its sub-resources, the devices, the senders, the receivers, the sources and flows, with a set of subsequent calls. And it will also begin to post regular heartbeats to the registry. The heartbeats are typically every few seconds, every 5 seconds is a recommendation. If the registry doesn't receive a heartbeat for a certain period of time, called the registry expiry interval, then it will actually deregister or let that node expire from the registry. And this is a way of making sure the registry always has an up-to-date list of all the currently connected resources to the network. So what does the registration API actually look like? What's actually going over the wire? Because we're going to talk about the scalability and performance of these operations. What are we actually measuring here? So over the wire, a registration API request is a simple HTTP post operation. So this is a RESTful API, and we're just basically sending some human-readable text over the network. The payload there is a JSON, some JSON data, which includes some information like the host name, a description of it, and the endpoints available on that node. The response from the registry is a simple message saying that the endpoint, that database entry has been successfully created with a URI for that. The heartbeats are even smaller. It's just a simple HTTP post operation for the node letting the registry know it's still connected to the network, and the registry will reply with a response saying, okay, I hear you, and here's a timestamp to confirm. So now moving on to the IS-04 query API. This time, this is used by the client, so the broadcast controller or the routing panel or whatever. And the purpose is here that it can get a list of all the registered resources from the registry, so it could then populate its user interface with those senders and receivers that are available on the network. So it does that using the IS-04 query API. A feature of the query API is rather than having to poll the registry all the time to get an updated list of resources, you can subscribe to WebSocket notifications of changes in the RDS. So this is a well-known IT protocol, and every time something changes on the RDS, over the query API, the client will be made aware of that, and it can have a constantly updated list of resources. And that's just the query API polling the registry for its initial list there. Okay, now moving on to IS-05. So whereas IS-04 was for discovery and registration, IS-05 is for connection management. This is used by the client to make connections between the nodes. So it already has all the information it needs from the registry. So the processes that are carried out with the connection API are between the client and the media nodes. And first of all, if it wants to make a connection between a sending node and a receiving node, it will get the transport file by using the connection API of the node that has the sender as a sub-resource. This transport file is typically something like a session description protocol file. It's an SDP file, and it contains all the information that the receiver will need to make itself ready to receive the media stream from the sender. Things like, for a video, that could be the format, the frame rate, and so on. So once the client has received that transport file from the sender, it will patch it to the receiver, and then the receiver can make itself ready to receive the stream over the network and it can make a call to the network to join the multicast group by using something like IGMP join, and then using standard network technology, the switch or the network will make sure the packets start to flow from the sender node to the receiver node, and hopefully we get a picture on our monitor from our camera in this case. Again, let's have a quick look at the type of data that's going over the network that we're going to be measuring the scalability of. So in this case, let's have a look at the SDP file, because this is something new in this case. Again, it's just human readable text. There's not too much of it. So it's just a few bytes of data with information, like I said, about the format of the media that's going to be sent over the network. So now moving on to talk about our scalability study and how we set this up. So the point of the scalability study was really to make sure we can use these APIs at scale, because in real broadcast deployments, we might have many, many thousands of senders and receivers on our network, and we want to make sure that we don't kind of reach any bottlenecks in the system with all these APIs trying to be called at once. So within the AMWA, within the Advanced Media Workflow Association, we set up the NMOS Scalability Study to help address this requirement. And Sony volunteered to lead this study, and we got lots of feedback from others within the AMWA community on the types of experiments we should be doing. We chose with this study to use a virtualized network because it's the APIs we're measuring the scalability of. We're not actually looking at sending media over the network within this study. It's just all making sure all these API calls can be tested at scale. So we thought a virtualized network was a valid way of doing this and much more practical than trying to set up a physical network with many, many thousands of nodes on it just to measure the APIs. So the virtualized network we chose to use is called Mininet. This is an open source virtualized network that's available to use for free, and it allows you to simulate a very large number of network endpoints with a network topology of your choice. You start off with your physical host computer. It could be Windows, Linux, or Mac. And within that, you run the Mininet virtual machine, which is Linux-based. And by running some scripts within Mininet, you can set up a network of your choice. So this can have any topology you choose with any number of switches. You can optionally have a network controller for SDN control of that network. The important thing for us is we can have these separate, what we call Mininet hosts, attached to each switch. So many of these can be attached to each switch. And what these Mininet hosts are, they're basically lightweight containers, so they can run independent Linux processes on each. And they're separated by a virtual network interface card, a virtual NIC, using OVS switch technology to make sure they're kind of separated in networking terms. So within each of those NMOS processes, what we've done is within each of those Mininet hosts, what we've done is we've extended Mininet to allow them to run NMOS-based processes by extending that scripting language to make it very easy to run scalability tests with this network. And then using that, we run an NMOS registry on our first Mininet host and multiple instances of NMOS nodes on all the other Mininet hosts. And we've tried several implementations of NMOS registries and nodes. For the bulk of this study, we used our own open source implementation, which is called NMOS CPP. So we've got NMOS CPP registry and NMOS CPP node running on all the Mininet hosts. That's available for anyone to use. It's freely available on GitHub under the Apache 2 license, and we welcome lots of people to use it and contribute to it. And we used that for the bulk of our study. Once the system is all up and running, what we want to do is be able to make timing measurements. And we do this by using the log files that are generated by the registry. And in real time, using Logstash, we populate an Elasticsearch database, which can then drive a Kibana dashboard, which is able to draw graphs of things registering to the registry over time. And that's what we do to draw the graphs that we've generated in this study. So now to actually look at some of those graphs, let's look at the scalability study results. So the first test we did was an initial registration test. So taking anything from 100 up to 2,500 nodes on our network, with each node having 6 resources. So it's got the top level node resource, but each node also has one of each of the other resource types, the device, sender, receiver, source, and flows that I talked about earlier. How long does it take for all of those to register with the registry over the network? So in terms of resources, we've got up to 15,000 resources in that 2,500 nodes case. So this is quite a lot of different API calls happening over our virtualized network. The result we found was the total registration time scaled linearly with the number of resources. So as the number of nodes or resources went up, the time taken to register them went up at the same rate, and we've got a nice linear pattern there. So this was a really good result for us, because what we didn't want to see was some bottleneck when you get to a certain number of nodes, and this time to register going sky high in some sort of exponential pattern. So actually seeing a nice linear result like that was a good result. We then looked at the particular result with the maximum number of nodes there to see the pattern of registrations over time. So with 2,500 nodes, 6 resources per node again, that's 15,000 resources, you can see the total time to register was just over 3.5 minutes. So this was from starting up your network to having everything registered on the registry. But what we found was the rate of registration varied over time. So we've actually got quite a slow start for the first few nodes to get registered, and also at the end, for the last few to become registered, took a little while. And we call that a slow start and a long tail. And we wanted to study why this was happening, because ideally we shouldn't have this. So we looked at a smaller number of nodes, so we could repeat this experiment many times. And again, so this time 750 nodes with 6 resources per node. And this time we found the registration time was just over 50 seconds. Again, we had our slow start and long tail, and we looked into it in a bit more detail and looked at ways that we could remove that kind of performance and improve it. And what we found was the slow start was actually due to the discovery mechanism when the nodes are first trying to discover a registry on the network. So if you remember me saying earlier, discovery can either rely on multicast DNS or unicast DNS. And within this system, initially, we use multicast DNS. And that means the node and the registry have to have a series of exchanges between them to make sure that the node is definitely talking to a registry with the right registration service types and so on. And so the registry is having thousands of nodes, 750 in this case, all asking it questions at the same time, and can become quite overwhelmed. Sometimes doesn't manage to respond to every single node. And then the node will time out and try again a few seconds later. And what we found was the kind of default timeout in the Bonjour library that we were using was set to a very long period of time, about 30 seconds. So what we found was the ones that were timing out took a long time to get going again later on. So by reducing that timeout to something like 5 seconds, which is of a similar order to the heartbeat interval I talked about earlier, we found we could get rid of that slow start problem. The long tail was a similar issue. This was the HTTP post to the registration API that I spoke about earlier. And again, if the registry didn't respond to that HTTP post immediately, then the node would time out again and try again sometime later. And again, that timeout was set to a rather long period of time. We reduced it down to 5 seconds. And we found, as a result of these optimizations, you can see the slow start and long tail disappearing there. And we've reduced our total registration time from something like 50 seconds to less than 30 seconds. So the key kind of recommendation here is carefully look at your implementation and make sure that optimizations like that are carried out. The second thing we looked at was the recovery of the registry after a failure. So what we did in this case was with Mininet, we're able to virtually pull the plug on the registry. And initially we let everything register to the registry, and then we pulled the plug on the registry for just a 5-second period. So for 5 seconds, the registry was getting no heartbeats from any of the nodes. For a few cases, the registry would miss a second heartbeat for whatever reason, and it would deregister some of the nodes from itself, from the registry as a result of that. So what we found was just a few of the nodes ended up not being registered anymore, and they had to re-register themselves. And we found that within 30 seconds, all of those nodes that had expired from the registry were able to register themselves again, and we were back fully operational within our registry. If we pulled the virtual plug on our registry for a little bit longer, for 30 seconds, in this case, this is well over the registry expiry interval of 12 seconds, so we would expect all the nodes to become expired from the registry. And you can see that here. Everything that was registered is no longer registered, and it takes a little time for them to discover the registry again and then become fully registered, and we're back to 750 nodes on our network. So in this case, it took 1.5 minutes for everything to become fully registered again. So to get around these sort of issues, the recommendation is that you have multiple registries that are federated. So if one of your registries does go down for a while it's recovering and getting back to full registration, the other registry is still fully operational. So we then looked at this in a bit more detail. So in this case, we had 2 registries on our network that are federated with a 2-way federation replication. So everything that's on one registry becomes registered on the other over time with this federation mechanism. And we're looking here at the registrations on the second registry. It takes a little while to get going, and then it gets a kind of bump of registrations that it receives from the first registry. And then over time, you get a kind of linear response as some things register with that registry directly, and some of the registrations come over from the first registry. The good news is, as well as providing the redundancy I spoke of by having 2 registries, it also reduces the initial registration time. So we're now down from the 30 seconds that we'd reached with our optimizations earlier to 15 seconds registration time for all those 750 nodes on our network. So using multiple registries is definitely a good thing. The final result I'm going to talk about today is connection management at scale. Before you can start connecting things, though, the client has to get its list of resources from the registry using the IS-04 query API. So going back to our full number of nodes, the 2,500 nodes, so that's 2,500 senders and 2,500 receivers, how long does it take to populate the clients using the query API? Well, we found with some optimizations, we could get this down to less than a second. And the key thing to use here was the pagination option within the query API that lets you break down the number of resources into pages and get those one at a time. And this allows you to very quickly populate your client with the full number of nodes that are registered on the registry. We then want to test some connections between those nodes. So we selected 750 cross points at random, 750 senders and receivers at random, and tried to make connections between them using the IS-05 connection API, using this mechanism I spoke about earlier. In this case, those 750 cross points could be updated, and the connections made and the cross points updated on the UI of the client within less than 3 seconds. And again, this required some optimizations to get this down that low, using things like the WebSocket API that I spoke about earlier to make sure the client's updated using push notifications was important for this. So having gone through some of the results, you can probably imagine we have a few best practice recommendations, some of which I've touched on already. So I want to talk about those and how this TR 1001-1 document recently published by the JTM really helps us to make sure that some of those best practices are carried out. So the first one is really quite obvious, but it's to make sure all your media nodes across your network are actually using IS-04 and IS-05 to ensure we have full interoperability across our network. And sure enough, TR 1001-1 mandates the use of IS-04 and IS-05, as well as some other things like DHCP and DNS. So that's good news. We're definitely all going to be using IS-04 and IS-05 across all our media nodes. So the second thing that I mentioned earlier was using clustered or federated registries to improve the registration performance is a really good thing to do. Not only does it lead to faster registration initially, but also better fault tolerance. You've always got a backup registry there if one of them loses connection for a short while. So TR 1001-1 doesn't mandate that you use multiple registries, but it does certainly support it. The network environment shall contain one or more registries implementing AMWA NMOS IS-04. So we're certainly able to do that, and I'd highly recommend that people do that for anything other than a very small installation. The third recommendation I'm going to highlight is that we choose our heartbeat and registry expiry intervals carefully. So you saw earlier the kind of fault tolerance to pulling the virtual plug on the network for a few seconds. We found that the recommended values from the IS-04 spec of 5 seconds for heartbeat interval and 12 seconds for registry expiry interval actually work very well, and we couldn't get better performance by varying those. But that might differ on some different sizes of deployment. So ideally, you'd be able to specify your heartbeat and registration expiry intervals and make them configurable. Also, it's very important that we use the same heartbeat interval across all our media nodes. We don't want some of them heartbeating at different periods to others, because they've all got to match that registration expiry interval on the registry. So what we need to make sure is that they're all able to get that heartbeat interval from some common resource. Finally, the choice of the DNS SD and the HTTP timeout and retry intervals that I mentioned earlier, we found by reducing those to something similar to the heartbeat interval, 5 seconds, actually led to really good performance. So using the heartbeat for that as well is a good best practice recommendation. So where TR 1001-1 really helps with this is that the heartbeat interval is now stored in a centralized system resource that all the media nodes have to go and look at startup and access that heartbeat interval and use it. So by mandating that that's used, this kind of meets all these issues, this best practice recommendations we've got here. So the system resource is also discoverable using DNS SD, and it's some centralized resource on the network. It could be on the same endpoint as the registry, or it could be somewhere else within the system. And I think it's going to be a new AMWA spec IS-09 soon in the future. The final best practice recommendation really is to use Unicast DNS SD rather than multicast DNS. So I spoke about some problems with the startup time of nodes discovering the network using MDNS earlier. We found these could be partially resolved using Unicast DNS. Things got a lot quicker. Unicast DNS is also better for scalability, and it's actually essential if you're not within a layer 2 network and you've got a larger layer 3 network. You have to use Unicast DNS because MDNS does not scale across layer 3 networks. Multicast DNS has also been deprecated from IS-04 in future. So the good news is TR 1001-1 mandates that we should use Unicast DNS SD, not multicast DNS. So that will really help with scalability. That's a really big one for the scalability of IS-04 and IS-05 based deployments. So some resources, if you'd like to repeat any of these experiments, our Mininet test environment is now recently been made publicly available on the AMWA NMOS GitHub pages, NMOS Scalability. You can go in there, it tells you how to install Mininet and all the NMOS extensions that we've contributed. It's also got a link to a paper that we gave recently. This was at the SMPTE Annual Technical Conference that has more of the results that I've talked about today. So this was the paper that I wrote with Gareth Sylvester Bradley, and the paper itself has been generously made available by SMPTE on the IEEE Explore web pages, if anyone wants to read that and look at the results in more detail. I also mentioned earlier the Sony NMOS CPP open source software is free for everyone to use. Many vendors are now using it within their implementations, and it's free to use under the Apache 2 license. So if you want to have a look at that, look at the Sony GitHub pages. So it just remains for me to say thank you very much for coming. Thanks also very much to the team back in the UK who ran all these studies, led by Gareth Sylvester Bradley, and the team, Simon, Mark, and the rest of the team back in Basingstoke. Okay, thank you.
Rob, thank you very much. So we have time for a question, if anybody has anything. Yep.
With your scalability testing, I'm presuming that was done without any of the security mechanisms in place. How do you expect them to impact those numbers?
I would expect the security, the use of TLS and the certificates and so on to have some small amount of overhead, but again, it's mainly kind of text data. It's not, the payload isn't very much, so I wouldn't expect it to have a big impact. And I think again, it will be looking at how those operations can be optimized within your own implementation to make sure the overhead is minimal. I think the guys who have been studying the security have made sure that there are ways of making sure it can be scaled to large deployments, and I think one of Simon's white papers that he mentioned earlier on the BBC website actually addresses that issue, so hopefully there shouldn't be too much impact from that.
Okay, Rob, thank you very much.
Thank you.